In Alzheimer's disease, the strongest correlate of cognitive decline is synapse loss. The actin networks making up dendritic spines destabilize, and the spine collapses. To understand why, the field has focused heavily on a single protein, cofilin, and specifically on one regulatory switch, phosphorylation at its serine 3 residue. Here, the literature presents a strict contradiction. One laboratory shows amyloid-β acts through immune receptors to strip the phosphate off cofilin. This dephosphorylation destabilizes the actin network, killing the spine. An entirely independent laboratory shows that amyloid-β acts through Rho kinase to add a phosphate to cofilin. This hyperphosphorylation stabilizes the actin so rigidly that the spine is impaired and destroyed. Both groups measured human tissue. Both findings have been independently reproduced, and they point in completely opposite directions. The explanation for this is straightforward. Phospho-serine 3 is a degenerate mark. If a collapse in a spine and a rigidly locked spine both produce the exact same biochemical reading at the specific residue, then measuring that residue cannot contain the mechanistic truth of the disease. To see why the mark is degenerate, we have to look at the two pathways governing the spine's structure. RhoA drives contraction and spine collapse. RAC1 and CDC42 drive protrusion and spine growth. Notice the top bottleneck. Both the destructive RhoA pathway and the protective RAC1 CDC42 pathway converge on a single node, limb domain kinase. At the shared output below, both pathways write the exact same phosphate onto cofilin serine 3, despite producing opposite structural outcomes. A perfectly compartment-resolved measurement at a single synapse still wouldn't tell you which pathway reached the mark. The degeneracy is in the variable itself. To recover the true direction of synaptic change, we have to move one biological layer upstream to where the sign is actually set. One layer above the actin network sits effector 5. It is an exchange factor that balances the activity of the destructive RhoA pathway against the protective CDC42 pathway. Effector 5 is regulated by phosphorylation at tyrosine 361. Adding this tag shifts its connection toward RhoA, locking in the destructive signal. But this identical tag carries a second instruction. It acts as a beacon for UB3A, a ligase that binds the complex and pulls away. UB3A consigns effector 5 to the ubiquitin proteasome system, where the entire transducer is dismantled and destroyed entirely. A dendritic spine requires precise, highly localized structural instructions. Destroying the transducer itself guarantees the signal cannot outlast its utility. This establishes a core rule of the synapse. In a system where the activation mark is simultaneously the execution order, a protein's abundance and its kinase activity are not independent variables. This self-terminating design applies universally across the spine. We see it perfectly mirrored in the opposing protective arm, the Reelin signaling pathway, and its central adapter protein, disabled 1. Disabled 1 operates on the exact same paradoxical logic as effector 5. When a signal arrives, a kinase called FINE writes a tyrosine mark onto disabled 1, successfully transducing the protective Reelin pulse. That identical mark immediately tags disabled 1 for proteasomal destruction. This dual function creates a severe systemic fragility. The synapse lacks a standard chemical off switch that isn't a protease. The temporal control of a healthy synapse relies entirely on the cell's proteolytic clearance services, working with perfect substrate accuracy. The prevailing explanation for Alzheimer's disease is a general loss of protein clearance in the aging brain, but a simple decline in clearance capacity cannot explain the mechanics of synaptic failure. Alzheimer's synaptic execution is a lesion of proteolytic specificity. The proteasome is executing the wrong instruction. When amyloid-β infiltrates the synapse, it specifically targets and binds to the licensing kinase FB2. Amyloid then rapidly triggers the immediate proteasomal degradation of the FB2 receptor, completely dismantling it before it can signal. FB2 is the specific kinase that writes the execution order onto tyrosine 361 of effector 5. With the kinase destroyed, the license to destroy the effector is never written. This diagram charts the exact consequence measured in human Alzheimer's patients. Because FB2 experiences too much destruction, the effector 5 it was supposed to condemn accumulates in the hippocampus, receiving too little clearance. The proteasome itself is perfectly intact. It is merely destroying a receptor the cell needs, while sparing a toxic substrate in the exact compartment where it should be clearing it. The protective side of the spine is neutralized by a separate failure in a different cellular disposal service, the endosomal lysosomal system, which handles the Reelin receptor, ApoE2. Decades before the first amyloid plaque forms, the absolute earliest known structural change in Alzheimer's disease is the enlargement of the early endosome. This diagram maps the failure at that exact sorting fork. The two most common genetic risk factors for Alzheimer's, SORL1 mutations and ApoE4, sequester the protective ApoE2 receptor inside these swollen early endosomes. The protective receptor is not absent or mutated, it is physically trapped in the wrong compartment. A sequestered receptor cannot transduce a second signal. The spine's protective arm is neutralized through a localized trafficking failure rather than a primary signaling deficit. If the sign of the synapse is set by destruction at the tyrosine and read out degenerately at the serine, we can test this model by comparing those two marks in the same human cortical synapses. This chart plots that prediction. In the control sample on the left, tyrosine 361 gates the GTPase state, which sets serine 3. The two marks rise and fall together in a tight linear covariance. In an Alzheimer's brain, serine 3 phosphorylation becomes driven by chronic ligand occupancy and unlicensed exchange factors, bypassing the tyrosine gate. The visual proof is the right-hand plot. The two residues violently decouple. The dispersion of the serine mark scatters randomly, shattering the covariance. If this decoupling occurs in human tissue, measuring total protein levels or downstream marks like pSer3 to validate a drug is clinically blind. This architecture immediately rules out phosphatase-directed therapies. Stripping a phosphate mark resets the signal, but it leaves the physical core of the toxic effector sitting directly in the dendrite. It also rules out global kinase inhibitors, specifically those targeting FINE. Inhibiting FINE halts amyloid toxicity at the synapse, but FINE is also the exact enzyme required to write the protective Reelin pulse. The intervention is sign-ambiguous, disabling the poison and the antidote simultaneously. The model points instead to the trap itself, the endosomal sorting clock. Since the protective receptors are physically present but sequestered, the goal is to fix the compartment environment rather than the signal. We see the proof of this strategy when researchers inhibit NHE6, the endosome's proton leak channel. Correcting the internal pH of the endosome completely reverses the sequestration of ApoE2, restoring the protective Reelin signaling. Repairing the compartment restores the capacity to signal without adding a drug or blocking a kinase. To halt Alzheimer's synaptic execution, the field must stop trying to supply chemical signals the neuron can no longer clear, and instead repair the biological clock that processes them.